So exponents is one topic which we already discussed in the previous sessions in the lower classes. Let's revisit exponents because some of its properties are very important in understanding this topic. So revisiting exponents. What are exponents? What is it about the word exponent in mathematics? Exponents are those numbers which are expressed in power form. The most simple thing is that if I have, say, 8, I can write this as 2 power 3, which is called the exponent form of writing the number 8. This is how we understand exponents. It's very simple that I can write this as 2 power 3, and therefore 8 expressed in exponent form is 2 raised to 3. So using the exponents and the base, I generally have exponent which is written in the form a raised to the value b. In this case, this is said to be the base and this is said to be the exponent, which makes me understand that exponent is nothing but the power form, the power. So this is the base and this is the exponent or power. We indirectly also sometimes refer to exponent as power, is what I understand exponent. So sometimes we need to find the importance of exponents in mathematical problems. So what is the significance of exponent in math life? Exponents help us in simplifying the values usually when multiplications are considered. Say for example, if my question is to find 16 times of 64 without actual multiplication. The actual multiplication would be quite easy if you take a calculator and type and you get the answer, or sometimes by just doing it with the multiplication process. But if my question was to find this without actual multiplication, then that would definitely include exponents connected to identifying the value of the multiplication, as out here 16 times of 64. So let's take this and see how I can do it without actually multiplying the two values. Now let me take the first value, which is 16, which can be written as 2 times 2 times 2 times 2, which gives me 2 power 4, 2 raised to 4. So 16 can be written as 2 power 4, and similarly I take the second value, which is 64, and this can be written as 2, 3, 4, 5, 6. I can write this 6 times so that I get this as 2 power 6. So in this case, my value 16 times of 64 indirectly can be written as 16, which is in exponent form as 2 power 4. So 2 power 4 in its exponent form, and 64 in its exponent form is 2 raised to 6. So I get this as 2 raised to 6. And therefore, this by law of index, the first law of index, a power m into a power n is a power m plus n. Therefore, this finally gives me 4 plus 6 is 2 raised to power 10, is what is the value I get when I multiply this with this. Now this is called the exponential answer for the given problem. Now how do I find the general value of this? It is simple that I take this 2 power 10 as 2 multiplied 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So I take them differently by taking 2 2's 4, 4 2's 8, 8 2's 16, 16 2's 32, 32 2's 64 times 2 128, 256, 512, 1024. So every time I double the value, what I get, whatever I get here, I double here, double, 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 double. So 10 times you double 2, finally I get 1024. Now this is strictly done without the actual multiplication. If my actual multiplication, let's see if I get the exact answer for verification through 64 times 16, 6636, 4 ones 4, and 6, 4, 12, and this is exactly the same answer. This is by actual multiplication and this is by exponential form. Is how we understand the significance of exponents in real life. So logarithms are always said to be connected with exponents. No exponents, no logarithms, and no logarithms, no exponents. So therefore, when we have discussed about exponents, revisiting exponents from the already learned topics from the lower sessions, then now we are going to see how logarithms and exponents are connected through a revisit of logarithms. So revisiting logarithms, I just have one of the most important property which connects logarithms with exponents, and it is this. So these are the two important formulae which connect the exponents with logarithms. That is, when log a to base b is c, the value of log a to base b is c, then when you convert this to exponential form is indirectly read as a equal to b power c, where here in this case b is the base, c is the exponent. Therefore, when I just connect this with the left hand side of the property, I see that the base will be the base of the logarithm and the exponent will be the value of the logarithm. So when I connect these two things onto the left hand side, I understand that base of exponent is nothing but base of logarithm out here. So base of exponent will also be the base of the logarithm, and secondly, exponent or power of this exponential equation will be nothing but the value of logarithm. Of course, here this being c and this being b is how I understand the difference between the base and exponent, between the logarithms and exponential equations. So these are the concepts through which I can convert any logarithm value into the exponential form or any exponential form into the logarithmic form. So let's see the laws of logarithms. There are different properties, just as we have seen recently. Log a to base a is 1 and log 1 to any base is 0. Similarly, there are many properties connecting logs. The most important being log ab is log a plus log b, and log a by b is log a minus log b. So let's see the properties which we can prove using exponent formulae. So initially, the first law states that log xy is log x plus log y. This is what is the first property of logarithms. Log xy to the base a is log x to base a plus log y to base a. We can split the product in the log splits as the sum of the logs. So let's see how we can do that using a proof. Now, because x and y are given, let me take x and y in the exponential form. So let x equal to a power n and y equal to a power m, where a is greater than 0 with a greater than 0 and a not equal to 1. Then immediately I have x equal to a power n implies log x to base a will be n by using the form of exponential connected to logarithms, the formula as taken in the previous session, and this would give me log y to base a equal to m is what I get with the two different properties from this. Now because I want to find log xy, let me consider initially with xy. So x into y as taken from here would indirectly be a power n times a power m, because x is a power n and y is a power m. Substituted and the product gives me a power n times a power m. This, using the first law of index, gives me a power n plus m because the bases are same. Therefore x into y is a power n plus m, implies I apply log on both sides so that I get log applied on the left hand side to the base a gives me this, and log a power n plus m to the base a, where log is applied to the base a on both sides. Now after I apply the log on both sides, then I can simplify this to be simplified further so that I get log xy to the base a is nothing but this comes out, because we know that log a power m is m log a, the formula which says that log a power m is m log a. The power comes as the base outside the log. So using that, I get n plus n times log a to the base a. This is strictly by using this formula. Now when I continue with this, the left hand side becomes, implies log xy n plus 1 times of 1, because log a to base a is already proved to be 1 just now, since is 1, as we have already proved that. So in this case, finally it reduces to log xy to the base a is n plus m, but when n and m are individually substituted out here, I find that n is log x to base a. So in place of n, I have log x to base a. In place of m, I have log y to base a, when substituted individually for n and m. Therefore, finally, I conclude that my left hand side, which is log xy to the base a, is log x to the base a plus log y to the base a, thus deriving finally a formula which states that log ab is log a plus log b, provided the base is same. So the product comes out as the sum, is how we understand this property. Now coming to the second law, the first law of logarithm is what we have seen in the previous case. Similarly, we will see the second law of logarithm, which states that log x by y to the base a will be log x to the base a minus log y to the base a. So when I take the division comes out as subtraction, the multiplication comes out as addition, is how we understand the properties. So similarly, this can also be proved, and it's quite easy, because in case of this, I use the condition a power m into a power n is a power n plus m, but in this case, when I take x by y, I get this to be a power n by a power m, which comes as a power n minus m, the rest of them being similar. So this is the hint I can give in understanding this proof, as similar as the proof 1. So wherever I had x into y, I got a power n plus m, but wherever I want x by y, I get a power n minus m, the next law of index, and through this I derive where everywhere I get minus. It is as similar as the first proof, the only difference being that here I considered the multiplication, but here I'll consider the division, the rest of the proof followed by the division on the every step. Now with this second law of logarithm, which states that log x by y to the base a is log x to the base a minus log y to the base a. Now here I halt, because I have been using log a power m is m log a, but what if I wanted to prove this using the exponents? I don't want to use this formula here. Then how do I prove this using some other property except using this? Because I assume this to be a property which I don't know, then how do I use exponents by not using this exclusive formula of logarithms? So let's see just with a one statement out here in case of reconsidering this, where how do I get this statement? Now just I take this x into y as a power n plus m, through which I'm going to derive this part. I'm going to prove this using directly without using the formula log a power m is m log a. So in this case, when x into y is a power n plus m as taken from this statement, then I understand through the property that when x is a power n, then log x is n. Log x to the base a is n. Coming to the initial property, when x is a power n, this base will form the base for the log, and then xy comes here, and then n plus m. This is connecting the logarithms with the exponentials, the formula which we already taken in the previous case. So this is how I get the property here without using the formula. Connecting exponents directly with logarithms, I get this. Is how I understand the proof. Now let's see the third law of logarithms. The third law says that this is m log x to the base a. So the power inside the log comes out as the base when it comes out of the logarithm, is what we're going to prove as the third law of logarithms using the exponents. So we have already taken that x is a power n. So using this, immediately when I convert this into the logarithmic form, I understand that this is n is log x to base a. When I convert this exponent to logarithmic form, I have n equal to log x to base a. Now, that implies, because I need x power m, I'm going to raise this x to power m, so that equally on the right, this gets raised to power m. And this would be nothing but a power nm. Both the powers get multiplied, but this doesn't become n power m. Most of them do the mistakes out there. So this is a power, this is a power. So the powers get multiplied. So n times of m is a power nm. That implies, finally, I get x power m is a power nm, so that when I convert this exponential to logarithmic form, a equal to b power c, then log x power m, this forms the base. So to the base a will directly be equal to nm. This forms on the right hand side. This goes to the right hand side. Therefore, this exponent gets converted to the logarithmic equation as log x power m to the base a equal to nm. Now this in turn, when substituted, gives me that log x power m to the base a is n. What is n? I have n as log x to the base a times of this m is as it is, because I don't have any value for m. I just straight away take m in the next step. Now this, when rearranged with the terms, gives me log x power m to the base a is m log x to the base a, thus proving the third law of logarithm using the exponents connected with logarithms. So finally, I can conclude saying that the third law of logarithm states that log x to the power of m to the base a is m log x to base a. It is a very important formula in mathematics part. Now, I wanted to find some of the logarithmic problems using the different properties as we have identified, especially the three laws of logarithms. So when I wanted to find, say, the log of 343 by 125, then I just use some of the properties here. Clearly, this is in the form x by y. So my second law of logarithm says that log x by y is log x minus log y. And therefore, this can immediately be written as log 343 minus log 125 is how we understand. Now, one important thing out here in this question is that there's no base given. So remember, when there's no base given, we understand that this is referred as log to the base 10. When there's no base given, we understand this as to the base 10. So we don't need to put the base, indirectly assumed as to the base 10. So this being log 343 to the base 10 minus log 125 to the base 10 can further be simplified, because 343 can be written as 7 cube minus log 125, which can be written as 5 cube, which on further simplification using the third law of logarithm says that log x power m is m log x. Therefore this m comes out, this 3 comes out, 3 log 7, 3 log 5. Minus log 5. So I have to just simplify them using the different types of logarithmic properties, and then simplify further, finally to get the answer. This cannot be simplified further. So this is assumed to be the final answer for the given problem. Now what if I give this and ask you to find this, the reverse process? Can we do that? Is what we're going to see in the next example. Say for example, this is my question. I want to simplify this as a single logarithm where I have to simplify all these values. It's quite simple, because here I'm going to go in the reverse process of using the formulae. If my log x power m is m log x, then my m log x is log x power m. Therefore, my m log x becomes log x power m, written as 3 raised to 2, minus 4 log 2 can be raised as 2 power 4. And this remains as it is as log 5, which can be further simplified. Now this clearly makes me understand that log a minus log b is log a by b, the second law of logarithm. Therefore this can be written as 3 square by 2 power 4 as using the second law of logarithm, plus log 5 remains the same. So in this case, when I further simplify this, I get this to be log a plus log b as log ab, the first law of logarithm. Therefore, this can be written as 3 square by 2 power 4 times of 5 using the first law. Then finally, I simplify this answer so that I get 3 square is 9 times 5, 2 is 4, 4 is 16, so that this reduces as a single logarithm. 45 over 16 is the single logarithm value for the given problem. So we can do either by converting the single logarithm into split form, or the split logarithm into the single logarithm form by just using the properties, especially the 3 laws of logarithms. Now we'll see the applications of logarithms in real life, how scientists use logarithms in calculations, or how different branches of sciences use logarithms in real life. So the first application starts with using logarithms to find the magnitude of the earthquake, which is very important, because prediction of the magnitude of earthquake is very important before a major disaster is controlled well in advance. So to start with applications of logarithms, let's start with the first application where I use logarithms in calculating the magnitude. So the first formula is m is log I by s, where m is said to be the magnitude of the earthquake, and then I is said to be the intensity of the earthquake tremor. of earthquake tremor, and S is said to be the intensity of threshold earthquake. So let's see how we can connect and find the magnitude. So for example, my question is, if the threshold if the intensity of the earthquake tremor is 10 times the intensity of the threshold earthquake, then I had to find the magnitude of the earthquake. Then find its magnitude. So if I wanted to find the magnitude using the minimum information out here, it clearly says that the intensity of the earthquake tremor is 10 times the intensity of the threshold earthquake. So that I is said to be 10 times of S. As can be clearly seen from this equation, the intensity of threshold earthquake being S, I is 10 times of S. Therefore, when I have the magnitude, which I need to find here, because the question says about finding the magnitude, I clearly have the formula connecting M, I and S. M equal to log I by S to the base 10 of course, the common logarithm. Now this, on simplification, gives me I, when substituted with 10 times of S, gives me 10S by S, so that S gets cancelled both in the numerator and the denominator, and therefore I get this to be log 10 to the base 10, which is 1. Therefore M is 1. That implies my magnitude of the earthquake is said to be 1. The magnitude of the earthquake is 1, is how I understand connecting logarithms with real life. One of the applications of logarithms is connecting the intensity of the earthquake with the magnitude using logarithms. Now let's see the second application of logarithms in real life. As we have seen with magnitude of the earthquake, which can be calculated using logarithms, similarly there's one more application of logarithms in the branch of sciences. So let's see the second application, which connects the pH, which is called the acidity of the solution of the concentrated solution, which can be calculated using logarithms. As you can see in your chemistry class, we all know that the pH is connected with logarithms using the equation pH equal to minus log of H plus, where pH is referred to as the acidity of the solution which is considered in the experiment, and H plus is referred as the hydrogen ion concentration in that particular solution. So this is hydrogen ion concentration in that particular solution. So using this, let's see how we can connect this with real life. So for example, I have an example problem where I calculated if the pH of a tomato, say for example, the pH of a tomato is 4.2, that is the acidity measure for a tomato is estimated to be 4.2, then the question is to find its hydrogen ion concentration. So for the pH of a tomato, which is 4.2, what is its hydrogen ion concentration is the question out here. So this clearly relates that I have to connect with this logarithmic equation where I have the pH of a tomato is given to be 4.2. Clearly, the pH of a tomato is given to be 4.2. And the question is to find the hydrogen ion concentration, which is H plus, is the question. So let's reconsider the logarithmic equation. pH is minus log of H plus, which when substituted respectively for the values gives me pH is 4.2 is negative times of log H plus, so that when I rearrange the terms I get log H plus is negative times 4.2. Of course, this being to the base 10. Now this is a logarithmic equation which I want to convert to the exponential form. How do I do that? So this can be converted as log a to base b is c. So a is b power c. So this forms as the base of the exponent. So this is the hydrogen ion concentration, which can be calculated using a calculator. So the hydrogen ion concentration of a tomato with its acidity 4.2 is 10 power minus 4.2, as can be calculated using a calculator, is how we get the value connecting logarithms. This is one of the applications of mathematics or logarithms in real life.